Hello, I will proceed with the presentation on direct injection of drugs into remnant tumor cells after tumor resection using hydroporator. I am Seung Lee. I will start my presentation. The order of presentation is as follows. From figure 1, we can see there are many new cases of cancer in the world and the death due to the cancer. Figure 2 shows cancer case and death statistics for 2020 and project numbers for 2040, indicating an expected increase. Research is crucial for improved cancer treatments. Surgery, radiotherapy, chemotherapy, and targeted therapy are commonly used for tumor treatment. Surgery is the primary treatment for removing tumor masses. Radiotherapy utilizes high-energy radiation, while chemotherapy uses drugs to kill cancer cells throughout the body. Targeted therapy blocks cancer cell growth with specific molecules. After surgery, radiotherapy or chemotherapy aims to eliminate or reduce cancerous growth. However, aggressive tumors have high fatality rates, and existing treatments may yield poor outcomes in relapse. Drug delivery systems, a form of targeted therapy, are researched to enhance cancer cure chances. They deliver drugs directly to tumors, increasing concentration in cancerous tissue while minimizing side effects on healthy cells. First methods for drug delivery system is nanostructures. As shown in figure 3, nanostructures could be utilized as delivery agents by encapsulating drug or attaching therapeutic drugs and deliver them to target tissues more precisely. Second is gene therapy. Gene therapy directly delivers the oligonucleotides or nucleic acids to cancer cells and inhibits them at the gene level. It is alternative to common radiotherapy or chemotherapy. However, these methods have low throughput, toxicity, inconsistent delivery performance, time-consuming, and labor-intensive. Membrane disruption techniques like electroporation, optoporation, and microinjection create temporary nanopores for molecule delivery. However, these methods have drawbacks such as cell damage, inconsistent delivery, and limited scalability. Figure 4 shows the mechanism of disruption techniques. On the other hand, hydroporation, which uses microfluidics, provides an alternative approach to membrane disruption. It has several advantages: high throughput, delivery to multiple cells simultaneously, and reduced toxicity by avoiding potentially harmful components. Simplicity and cost effectiveness without requiring complex apparatus or vectors. Reliance solely on fluid flow without external energy. Maintenance of high cell viability and straightforward intracellular delivery. Moreover, hydroporation has potential for targeted delivery to residual tumor cells after tumor resection, minimizing off-target effects and preserving healthy tissues. Figure 5 is showing the short mechanism of hydroporation. The methodology used in this study can be explained as cell membrane disruption occurring in the T-junction channel. The cancer cells are formed in clumps in tissues. The fluid that contains drug flows to cells due to fluid flow. Cells are stretched hydrodynamically. This cell deformation process results in expulsion of cytosol to the cell's surroundings, producing transient discontinuities in the cell membrane. While cells recover their original spherical morphology, the influx of surrounding fluid into cells leads to convective transport of external materials into the cytoplasm. The cell resume their membrane disruption. It takes typically within 2 to 3 minutes. To assess the feasibility of cell deformation and temporary opening of cell membrane using fluid flow, magnetic beads are employed for observation during hydroporation. If the magnetic bead enters the cell through hydroporation and is subsequently attracted by magnetic field, it confirms the hydrodynamic conditions such as fluid flow direction, flow rate, and exposure time required for hydroporation in a fixed cell state. Once a sufficient flow rate to open cell membrane is determined, the effects of membrane disruption on the cells and any potential side effects need to be examined. This includes assessing whether the transient disruption of cell membranes impacts cell behavior or if the drug has an effect on tumor cells. Furthermore, the development of appropriately shaped injection channel is necessary for the device. The channel should have a circulating structure, allowing cells to be deformed in a fluid where sufficient cell death is not achieved. Afterward, the flow of the fluid is halted to facilitate the injection and absorption of the drug into the cells. Examples of suitable shapes for the channel could include tube-shaped or chamber-shaped configuration. To maximize the potential of hydroporation, certain limitations and considerations must be addressed. Optimizing parameters like fluid pressure, exposure duration, and compatibility with different cell types is crucial for safe and efficient delivery. Maintaining cell viability, controlling injection volumes, minimizing mechanical stress, and addressing potential side effects and membrane disruption are important aspects of experimental design. In cases where the fluid flow pressure alone is inadequate for transiently deforming the cell membrane, combining hydroporation with other techniques such as electroporation, optoacoustic poration, microinjection, or spike-like structures may be necessary. Successful implementation of this project could revolutionize clinical trials by improving drug response in various diseases. It also holds potential for personalized care through targeted clinical trials. In the early stages, these implications are expected effects. Furthermore, upon successful completion of the final stage, it could enable reliable removal of tumor cells after tumor resection through direct injection without harming surrounding healthy cells. This approach allows for selective removal of tumor cells while preserving normal cells. Additionally, it could be applied to targeted radiation therapy by injecting nanomaterials for more precise and effective radiation treatment. These are the references that I referred for this project. Thank you for your attention.